How are you doing this morning, Taylor?
Doing good. How are you doing?
Doing great. Let's see. Excuse me. Pull something up real quick. Alrighty, let's see. All right. So today we are going to actually start analyzing we're going to start with a YY circuit. So let's say that we have the following circuit. Excuse me. So this is our Y connected source. A, B, C, and neutral connections. That means this guy is VAN, this guy is VBN, this guy is VCN, and then over on this side we'll have our load. Capital N. And then we're also going to have transmission lines here in the middle, and we're going to start with them having some impedance. So I'm labeling it as ZWA for the impedance of the wire across the A phase, ZWB for the impedance of the wire across the C phase, or B phase, excuse me, and ZWC for the impedance across the C phase. And lastly, we are going to have a wire connecting our neutral terminals, which I'm going to call ZN, or that has some impedance ZN. So our neutral conductor may have some impedance. So we have a Y connected three-phase source and a Y connected three-phase load, where the intermediary is transmission lines. So let's talk explicitly about what it means if a circuit is balanced. So for a three-phase circuit to be balanced, all of the following criteria have to be true, okay? So the first criterion is the magnitude of the phase voltages at the source are equal. So this would explicitly mean then that the magnitude of VAN is equal to the magnitude of VBN is equal to the magnitude of VCN in our system. Our second criterion is that the phase separation between the voltages is 120 degrees. So we would see that the angle of VAN is equal to the angle of VBN plus 120 degrees. Is equal to the angle of VCN plus 240 degrees, so that all three are separated by, excuse me, 120 degrees, and this is for a positive phase sequence. Or we could have that VAN, or the angle of VAN is VBN minus 120 degrees, or VCN minus 240 degrees for negative phase sequence. So that's what's balancing our source. So a source is balanced when all the magnitudes are the same and there's a phase separation of 120 degrees, which is what we discussed yesterday morning. For our transmission line to be balanced, we need the transmission line impedances to be equal. So we could say that ZWA must be equal to ZWB must be equal to ZWC, and we can all set these equal to a common expression impedance Z wire. Note that the neutral impedance Zn does not have to be the same as the transmission line impedance for this system to be balanced. It's a special conductor, and if you actually look at the NEC code, the National Electronics Code, the rules for specifying the size of the neutral conductor are very, very different than the transmission line conductors. So I'll just make a note of this here. Zn does not have to be equal to Z wire. It can, it just doesn't have to be. And lastly, on the load side, for us to have a balanced load, that means the load impedances must be equal. So ZYA would be equal to ZYB would be equal to ZYC. And we could just represent all of these with a common nomenclature ZY. So under these four constraints, our system is balanced. And that's actually going to give us some very interesting information regarding the behavior of a three-phase circuit in a minute. So we can determine what's going to go on in our system by looking at our line currents. So let me go up here real quick and define what our line currents are going to be. So you may recall from yesterday that our definition for our line current was that it was the current flowing through the transmission line. So I'm going to call those guys I lowercase a, capital A, IBB, ICC, and we'll need this guy as well, INN. So these are our line currents, and I'm also going to make one other assumption here. And what I'm going to do is I'm going to say that our source side neutral is going to be our reference node for our analysis. So that point of interconnection between all of our voltage sources is, it may not necessarily be physically tied to ground, although it usually is, but it's going to be our reference for this particular system because ground, a true absolute zero voltage, isn't typically part of a three-phase system. So if we look at this circuit, we can write a Kirchhoff's current law equation, hopefully pretty easily, and we can see that IAA, IBB, ICC, and INN must all sum together and equal 0. And that's us effectively performing KCL at this node here. So the load side neutral. So I'm just going to go ahead real quick and write that down. And we can use Ohm's law to rewrite those line currents in terms of our voltages. So for instance, this current IAA, the current flowing through the impedance ZWA plus ZYA, would simply be this voltage drop V lowercase a, lowercase n, our phase voltage for the source over the A phase, minus the voltage at the node that I have the arrow drawing, which would be V capital N, lowercase n, divided by the total series impedance. So I'm just using Ohm's law with these voltages that I have defined in our circuit. And from this, I get VAN minus V capital N lower n divided by ZWA plus ZYA plus VBN minus VNN divided by ZWB plus ZYB plus VCN minus VNN divided by ZWC plus ZYC. And I'm going to do minus right here because I'm having everything in terms of V capital N lowercase n. And so V capital N lowercase n is the exact same thing as negative V lowercase n capital N. So if I switch the order of my subscripts, it's like changing the polarity of my voltage. So V capital N lowercase n divided by the impedance of our neutral conductor is equal to 0. All right, so if our system is balanced, we know that ZWA, ZWB, ZWC are all equal. Similarly, ZYA, ZYB, and ZYC are all equal. And so what we'll find is that V capital N lowercase n divided by Zn will be equal to VAN minus VNN over Z wire plus ZY plus V VN minus VNN over that same denominator, Z wire plus ZY plus VCN minus V capital N divided by Z wire plus ZY. And we can factor out VNN, and that will give us VNN multiplied by 1 over Zn plus 3 over Z wire plus ZY is equal to VAN plus VBN plus VCN divided by Z wire plus ZY. All right, so first off, has there been any of this symbolic math that isn't making sense yet? All right, well, if our sources are balanced, then that means VAN plus VBN plus VCN is the same, and I'm going to assume a positive phase sequence here. This would be equal to VAN times 1 angle 0 degrees plus VAN times 1 angle minus 120 degrees plus VAN times 1 angle minus 240 degrees. Or VAN times 1 angle 0 plus 1 angle minus 120 degrees plus 1 angle minus 240 degrees. So if anybody has a calculator handy, could you please add up those three complex numbers for me and tell me what the result is? So I'm specifically asking about this bit. Alrighty. Maybe you guys don't have a calculator handy, or you're not.
I do. It just took me a second.
Oh, no.
I just got 0.
Exactly right. So this means if the sum of VAN plus VBN plus VCN is equal to 0, that means that VNN has to be 0 as well. Because if the right-hand side of this equation is equal to 0, then the left-hand side of this equation has to be equal to 0. And 1 over Zn plus 3 over Zy plus Zy won't be 0 unless all of the impedances are 0. So this implies that VNN is equal to 0. And this is a very, very important revelation. So let's talk about this for just a second. So if we go back to our diagram here, if the voltage drop over this impedance Zn is equal to 0, then what does that tell us about the impedance Zn? So for a balanced system, we know for a fact that the voltage drop over Zn is 0. That means the actual impedance value of Zn doesn't matter, right? If the voltage drop is 0, then we can treat it as if it were a short circuit. Let's go ahead and look at a couple of other revelations from figuring out that the neutral to neutral voltage is 0. So our current flowing through the neutral conductor is, by definition, capital N, lowercase n, although it doesn't matter because it's 0, divided by Zn is equal to 0. So that means if the current flowing through there is 0, our neutral conductor is acting as both a short circuit and an open circuit at the same time. Now that may seem a little bit odd, but it is actually going to greatly simplify our future circuit analysis of YY circuits. We can also see that IAA, our line current through the A phase, is going to simplify to VAN divided by Z wire plus ZY. We could see that IBB, our line current through the B phase of our transmission line, is VBN Z wire plus ZY, which this is simply VAN times 1 angle minus 120 degrees divided by Z wire plus ZY. And lastly, we can see ICC is VCN divided by Z wire plus ZY, which is VAN times 1 angle minus 240 degrees divided by Z wire plus ZY. So these three results means that actually, I wrote it down a different way, so let's do it over here. So for a balanced three-phase YY system, our neutral current is 0. And this is, again, critically important that we keep this in mind in our analysis. Our line currents have equal magnitudes. And 120 degrees phase separation. So our line currents are balanced. What this means is that if we know one line current, we know all three line currents because we simply need to shift whichever one we know by 120 degrees to get the other two. If our line currents are 120 degrees, let's look at this system here, right? Taylor, since you were online yesterday, I will assume that you hopefully can answer this question. If not, it's not that big of a deal. But what would our phase current through our load be? So how would I define that?
Through like the entire load? Like all of them?
Let's say the A phase of the load.
It would would it just be the voltage drop across the single impedance?
Exactly.
Or is it
the current flowing through that? So A, capital N. What's the relationship between the phase current, or excuse me, the line current, I, lowercase a, capital A, and the phase current, I, capital A, capital N?
nothing? Like they're the same because
They're the
it's
exact same. Yeah. And we could do the same here, IBN and ICN. And so we can see that since we've proven that our line currents are balanced, meaning they have the same magnitudes and 120 degrees phase separation, our phase currents at our load are also balanced as a consequence of the line current balancing, right? Because if everything is in series, then if this guy is balanced, this guy must also be balanced. We can do the same thing for our phase currents at our source. I, lowercase a, lowercase n, I, lowercase b, lowercase n, excuse me, I, lowercase c, lowercase n. These are just negative of our line currents because they're flowing in the opposite direction, but they're still going to be just as balanced. So we can say then that our phase currents, all of our phase currents in the system, whether they're at the source or the load, have equal magnitudes and 120 degrees of phase separation. From this, we can also start to intuit things about the behavior of our phase voltages. So our phase voltages at the load. Using Ohm's law, our phase voltage at the load, which is going to be, I think I used green. There we go. So our phase voltage at the load is simply going to be our phase current through the load multiplied by the impedance of the load. So VAN is going to be IAN times ZYA, etc. And so we can see pretty easily then that our phase voltages would have equal magnitude and phase separation of 120 degrees. And let me write down some equations here just so you guys can see what's up. So VAN would be IAN, a balanced phase current, multiplied by ZY. VBN would be IBN multiplied by ZY, where we know that IBN is just IAN, but shifted by negative 120 degrees. And VCN would be ICN ZY, where that's just IAN times ZY shifted by negative 240 degrees. And we can also see that our line voltages at the load will have equal magnitudes and 120 degrees phase separation. So let's talk about those line voltages again real quick. So our line voltages defined to be the voltage drops between our transmission lines. This would be VAB. This would be VBC. And from here to here would be VCA. So from terminal C to terminal A. So we could effectively just write a simple Kirchhoff's voltage law loop, and we would find that VAB is VAN minus VBN. All right, so let me write that down. We can see that VAB is VAN minus VBN from this using the relationships that we just got. VBC is going to be VBN minus VCN is going to be IBN minus ICN times ZY. And I'm running out of room, so I'm not going to put a third one on that. But so if IAN and IBN are balanced, then the difference of them is also going to create things that are balanced by exactly a phase separation of exactly 120 degrees as well. So if we use all of these results we can develop a simplified model for a balanced three-phase YY circuit, which will make our analysis much, much easier. And so this is bringing us to our last topic of the day, the single-phase equivalent circuit. All right. So in our last example, we observed that for a balanced YY circuit, the voltage VNN was 0 and the current INN was 0. So that means that there's no voltage drop across the neutral conductor. We can treat it as a short circuit regardless of its impedance. This is true even if Zn, the impedance of our neutral conductor, is an open circuit, meaning even if the neutral conductor isn't physically there, we can still treat it like a short circuit. So we can actually split our balanced three-phase YY network into 3 independent single-phase equivalent circuits. So instead of analyzing that big ugly thing, we can have this. So this is the wire here. So these are our 3 single-phase equivalent circuits, and let's just talk very briefly about the information that we can glean from analyzing these pretty easily. So we should be able to figure out what line currents are pretty easily, and I might work an example that illustrates this momentarily. We should be able to figure out what our phase current through the load is easily, our phase current through the source is easily, and we should be able to figure out what our phase voltage over the load is. We don't need to figure out what our phase voltage over the source is because that's kind of given to us. So those are 4 critical pieces of information about the behavior of a circuit that we can get by looking at this as a single phase equivalent circuit. And then we can use these results and our original circuit in order to get effectively everything else. So let's analyze an example problem real quick to kind of put these relationships into use and then see how we can effectively manipulate things by understanding what a balanced 3-phase circuit means to get some other quantities. So example number 1, but it'll probably be the only example that works for today. So let's say that I have a YY system. And I'm just going to treat my neutral conductor as if it were a short circuit, so I'm not even going to bother making up an impedance for it. Z, Y. And let's say that the information that we're given is that VAN is equal to 200 angle 0 degrees volts RMS. The impedance of our transmission line is 0.05 plus J 0.01 ohms. And the impedance of our load is 3 plus J 2 ohms. I want to know what my line currents are and what my line voltages are at the load. So when I ask you guys a question on your homeworks, exams, and stuff like this, I'm never going to say find quantity I lowercase a capital A, which I guess I should go ahead and write these in before I forget about it. I'm going to ask questions exactly like that. Tell me what your line currents are. Tell me what your line voltages at the load are. Tell me what the phase voltages at the load are. Tell me what your phase currents are, that kind of thing. I'm never going to ask you for specifically like giving you a double subscript notation. And it's because knowing the specific value of one of them isn't particularly important. Again, once you know one of them, you know all of them. And in industry, they're not going to talk about the voltage across VAN. They're going to ask what's your phase voltage, what's your line voltage, things like that. So I'm trying to use the proper jargon to prepare you guys for jobs, internships, and all that kind of jazz. All right, so the first thing that I would do in a situation like this, though, is identify my line currents because I'm asked to figure them out. So that would be this guy IAA, this guy IBB, and this guy ICC, and also what my line voltages are. And so my line voltages would be VAB and VBC and also VCA. All right, so let's employ our single phase equivalent circuit method and get some information here. So we know that this is 200 angle 0 degrees. This is 0.05 plus J 0.01 ohms. This guy is 3 plus J2 ohms. Capital N, lowercase n. All right, so my line current, IAA. How would I go about solving for that? Do you guys have any idea? Oh, and this is volts RMS. So if we look at our single phase equivalent circuit, it certainly looks like we have a voltage source connected to two impedances in series. So I would argue that we could figure out what that line current is by simply taking our source voltage, 200 angle 0 degrees volts RMS, divided by the sum of our series impedances, 0.05 plus J 0.01 ohms plus 3 plus J2 ohms. And this will give us 54.753 angle negative 33.386 degrees amps RMS. Any questions on that astounding amount of circuit analysis I just had to do? I mean, the whole point of this single phase equivalent circuit is to break down this big ugly three-phase circuit into very trivial single phase circuits that you guys have been analyzing since way back in circuits 1. So these aren't trick questions by any stretch of the imagination. It's literally just applying steady state sinusoidal circuit analysis techniques. There's nothing remotely new here now that we have developed our single phase equivalent circuit. So if we wanted IBB, because we're asked for all of our line currents, do I need to do any circuit analysis whatsoever?
No.
No. I can take IAA, I can subtract 120 degrees from the phase angle, and I have the correct answer 100% of the time. So it's going to be 54.753 with an angle of negative 153.386 degrees amps RMS. And I can move right along and figure out what ICC is. So that's going to be 54.753. If I subtract 120 from that, that's going to be minus 273.386 degrees amps RMS. And boom, I have all three of my line currents just that simple. Now, in order to get my line voltage.
Actually, real quick, Dr. Hartman, do you have to subtract it, or is that just because you're assuming the negative phase separation?
I'm assuming a positive phase sequence with a negative phase. So I should have explicitly stated that. That's my fault. And I will.
Did you do either, or is it up to the person solving it, or does it have to be specified?
I usually specify it in the problem statement. I just didn't do it this time because I was making something up off the top of my head. In this class, I don't know that I ever actually give any problems that involve a negative phase sequence. Because again, it's just, is the generator spinning clockwise or counterclockwise? That's it. I mean, that's all positive and negative phase sequence really means. So as long as you're consistent, it doesn't particularly matter. But all of my solutions guides and all that kind of stuff use a positive phase sequence. But I also think that all of my problem statements explicitly say using either a positive phase sequence or an ABC phase sequence, which I think I described to be a positive phase sequence yesterday. But that is a very good question. All right. Yeah. So we're looking at, we're trying to figure out how to get our line voltages at our load. And line voltages don't exist in our single phase equivalent circuit because there's not two transmission lines to measure the voltage across in our single phase equivalent circuit, right? We only have that single A phase of the transmission line in our A phase single phase equivalent circuit, the B phase of the transmission line in the B phase of the equivalent circuit, etc. So what we're going to do instead is employ Kirchhoff's voltage law like we did before, and we could find that VAB is, again, this VAN minus this phase voltage VBN by doing Kirchhoff's voltage law around this loop. So if we know our phase voltages, we can easily determine our line voltages. So to get our phase voltages, let's say that we want VAN. What could we do?
Just the current IAA times the impedance of Y.
Yeah, that's perfectly acceptable. So using Ohm's law, IAA times VY, which would be 54.753 angle negative 33.386 degrees amps RMS times our impedance of 3 plus J2. I get 197.416 angle 0.305 degrees volts RMS. And so from this, the BN is just going to be 197.416 angle, let's see, negative 119.695 degrees volts RMS. And from these results, I know now that VAB, a line voltage that I'm actually interested in, is VAN minus VBN. And actually, so let's scratch this guy right here. Let's pretend we didn't understand that relationship. This is going to be skipping ahead to something that we're going to cover again on, let's see, if today's Tuesday, it's Thursday. So VAN minus VBN is our line voltage. Can we all agree on that based on doing a Kirchhoff voltage law loop around that thing I did in pink? I guess I shouldn't have erased it.
Yes.
Okay. So the reason why we don't actually need to know what VBN is and why it's maybe more important for us to not bother figuring out what VBN in this case is because we know that since this is a balanced three-phase circuit, we're going to have VAN minus VAN times 1 angle negative 120 degrees, again, because we're assuming a positive phase sequence. So that means VAB is simply VAN multiplied by 1 angle 0 degrees minus 1 angle negative 120 degrees. Or VAN multiplied by the square root of 3 angle positive 30 degrees. Just double check that that complex number relationship gives exactly that. 99.999% sure is correct, but can't hurt to check. Yep, square root of 3 angle positive 30. So what this has actually done is really given us a transform so that we can convert phase voltages into line voltages. Because if we know for a balanced system, if it works once, it's going to work every time. This is the definition here. So if we take, for our particular example, we have that, excuse me, 197.416 angle 305. Multiply this by root 3 angle 30. We get 341.934 angle 30.305 degrees volts RMS. And then we could shift this by negative 120 to get VBN, or excuse me, VBC, and by another negative 120 degrees to get VCA. So just understanding the relationships between these different, I'm trying to think how to put this. I guess it's not even understanding relationships between the different quantities. It's just understanding what it means to be a balanced three-phase circuit, recognizing that the B phase lags the A phase by 120 degrees, the C phase lags the A phase by 240 degrees, and things like that is actually going to allow us to greatly reduce the amount of information that we're going to need to know about any given circuit and still be able to analyze it. Alrighty. So on, let's see, on Thursday, what we're going to do is we are going to more formally develop transformations that will allow us to convert any balanced three-phase circuit into a balanced YY circuit. Because using the single-phase equivalent circuit is the easiest means by far of analyzing the three-phase circuit. If we didn't use a balanced YY circuit, what we would have to effectively do really is rely on setting up systems of equations using either nodal analysis or mesh analysis that would require computers to solve, because we'd have 3 to 4 equations with 3 to 4 unknowns, which our calculators can't do. But a single phase equivalent circuit breaks that down into this, in my opinion, trivial guy right here, where we can use Ohm's law and techniques like voltage division and things like that in order to get the results that we need very, very quickly. Okay, so thank you guys for showing up this morning, paying attention, all that jazz, and I will see you on Thursday if there's no further questions. I am going to be posting a homework assignment today. Right now, the expectation, it's going to be due a week from today, like all of them are. But right now, the expectation is that you will only be able to analyze the YY circuits, but we'll get into Y delta, delta Y, and delta delta, and all that jazz come Thursday. Yeah. All right. That's enough out of me. Any questions before I shut this guy down?
Will there be any additional extra videos you'll be posting on Moodle?
So I'm in a pickle here because I have so much program share crap to do for ABET I'm trying to catch up on grading you guys' stuff. And I'm trying to figure out what the heck I'm going to do in the fall. That it might just be live lectures like this for the remainder of the quarter, which is like 1 week. Do you have a problem with that? Or, I mean, if so, that's fine, and I can figure out how to
No,
do.
I don't. I was just curious because, like, I just noticed the change. So I just was curious.
Yeah, I got busy. So this is the point in the last quarter, where I also got crazy busy, and I didn't have any lectures pre-recorded, and I thought, oh, I'll be able to get ahead of it, and then I totally didn't. So I kind of pooped the bed on that one.
No worries. I just noticed it and I was curious if that was intentional or or not.
No, it's due to my procrastination and not staying on top of grading you guys' stuff. So sorry.
No worries.
All right, I'll catch you guys on Thursday.
Yeah, see you Thursday. Have a great day.